Bonjour. C'est un grand dommage que je ne parle pas français, mais j'espère que vous comprendrez l'anglais. So I had the pleasure and privilege to have dinner with the French group over here and the Prime Minister of France, the former Prime Minister of France, and I promised to start this way, and I did, yes. It's a great pleasure and privilege to be here with you to celebrate 60 years of science in Israel, and let's get started. I want to. The name of the talk is Pure and Applied Science, and the idea that I'd like to sell to you today is that there is no such thing as pure and applied science. In other words, there is such a thing as science, but there is no difference between pure and applied science. It's the same thing. Science is one entity which cannot be separated into different categories, into those two different categories. And in order to back that up, I'd like to tell you a little story. When I was an undergraduate, I studied at City College in New York. At that time, what is called pure mathematics was very much, I studied mathematics over there, what is called pure mathematics was very much the vogue, and people even looked, the more prominent mathematicians were a little contemptuous of any kind of application. There was a very famous, prominent mathematician in the first half of the previous century by the name of G.H. Hardy, who was in a branch of mathematics called number theory, and he said that the only thing he regretted having done was once that he didn't pay attention and he did some important work in mathematical genetics, and this is the only thing he regretted because it had some use. So this was the atmosphere in the late 40s of the previous century, and being a young man, impressionable, I was swept up in this atmosphere, and I also got into studying number theory. I don't want to go into the details of what number theory is. It has to do with prime numbers, with some of you may have heard of Fermat's last theorem, which was recently established after being an open problem for over 350 years. What attracted me and what attracted Professor Hardy in number theory were four properties that number theory has. One was that the problems in number theory are very natural. The second item was that they are easy to state. Very often a school child can understand the statement of a problem in number theory. Let me just give you an example. I knew this wasn't a good idea. They talked me into it, but it's not a good idea. Here we are. Good. That's it. All right. Number theory. Fermat's theorem. Okay, press the button. Okay, take a look at this. 3 squared plus 4 squared equals 5 squared, right? So we have, I think that's right, 9 plus 16 is 25, okay? Now, next button. That's it. Okay, what if we do this for, rather than doing it for squares, we try to do it for cubes? Are there 3 numbers, x, y, and z, such that x cubed plus y cubed equals z cubed? Well, people thought about this for a long time, and then they came to the conclusion that the answer is no. Next button. How about the 4th power, the 5th power, the 100th power, the 1000th power, any n? Is it possible to find x, y, and z so that x to the n plus y to the n equals z to the n? And this problem was open, as I said, this was suggested by Mr. Fermat 350 years ago, and it remained open for 350 years, not because people didn't work on it. They worked on it very hard for 350 years. Imagine that. Finally, somebody did it about 15 years ago. He proved this. Okay? So this is number theory. This is a problem which is natural. You mean the Egyptians already knew the first line over here. It's easy to state, yes. It is very, very, very difficult to prove. Very deep and difficult. And don't go away, don't go away. So we have 3 things. We have it's natural, it's easy to state, it's difficult to prove, very difficult, and it is, and this is the most important item, it is, or at least it seemed at the time, 50 years ago, it seemed absolutely useless. And that's what attracted me, okay? Yes, natural, easy to state, difficult to prove, and most important, absolutely useless. So when I got to do my doctorate, I got into another subject which is also seemed to me to have all these characteristics. Let me see if I can. Is this it?
We will change it.
Oh, here we are. Here we are.
You can look at the screen. We'll change the screen. Okay?
What's that?
We will change it on the screen from there. You just have to look on the screen. Don't look at the laptop.
But I have to change it.
You want to change it from here?
Who's going to change it? What do you mean?
Okay.
Let me do it. I'll change it for you. You know, ladies and gentlemen, I want to tell you this. You know, you heard about the Columbia disaster. Everybody here has heard, I think, about the Columbia disaster. There was an article in the New York Times several years ago which said that the Columbia disaster was caused by PowerPoint. No, it is not a joke. I mean, people got killed over there. It was caused because the engineers made PowerPoint presentations rather than giving more detailed lectures. You go, you press the button again and again. And the problem that caused the Columbia disaster was actually foreseen by the engineers, and it was discussed in presentations, but people didn't internalize it because it was PowerPoint. All right. Okay, when I did my doctoral thesis, I did it in an area it's called knot theory, okay? And knot theory, the problems are natural. Okay, and they're natural, they're easy to state, they're very difficult to prove, and they were also absolutely useless. Let me tell you what it is that I did, what is knot theory about? Well, here you have some pictures of knots on the screen, and you see what you have over here are alternating knots. Right? What do I mean by alternating knots? You see, when you look at these knots, you see that as you write them, as you make drawings of them, for example, take the top knot. So the purple one goes on the top, over the green one, and then under, and then over, and then under. Okay? So and the bottom one also. The blue one goes on the top, over the red one, and then under. These are alternating knots. Here we have, on the top, we have, again, two pictures, and one of them is not alternating. You see, it goes, the red one, which side is it? On one of them, the red one goes over the blue one, and then again over the blue one, and then twice under. So that's not an alternating one. But in the other one, the red one goes over, under, under. So that is alternating. Now, take a look at the bottom picture. The bottom picture has 3 knots, okay? We have a red, a green, and a blue. And if you follow those 3 knots along, you'll see that they alternate. The green one goes under the red one, then over the blue one, then under the red one, then over the blue one. And so all of them, yes? So we have here 3 knots. 2 of them are alternating, and 1 is not alternating. Now, the thing that I proved for my doctoral thesis was that alternating knots don't come apart. If you take a look at the one which is not alternating, you see that you can simply pull it out, right? You pull it out, the red and the blue will come apart. But the one that the other one are linked together, they will not come apart. The bottom one is not so clear whether you could pull it apart or not pull it apart, but one of the things I proved in my doctoral thesis is that alternating knots do not come apart, ever. They cannot come apart. No alternating knot can come apart. And you see, this problem is very natural. It's easy to state the problem, like the problems of number theory. It was very difficult to prove. I worked very hard at it, and it was not known before. And it is absolutely useless. You know, who cares? Yes. Right? Wrong. Okay? Wrong. I got the idea, the basic idea, after having worked on this for about 2 years, from 52 to 54, I got the basic idea, the breakthrough, the final idea that was needed to prove this theorem, which, as I say, is quite deep. Alternating knots don't come apart. While standing in a shower in Princeton, New Jersey, one evening in October of 1954. Now, in October of 2004, I'm sitting in my flat, not in the shower, I'm sitting in my flat in Jerusalem, and the phone rings. It's about 10 p.m. And on the line is my grandson, Yaakov Rosen, who's studying medicine in Beersheba, in the medical school of Beersheba. And he says, "Grandpa, can I pick your brains?" So I say, "Sure, Yaakov, what's up?" He says, "What are linking numbers?" I say, "Linking numbers? You mean like in knot theory?" He said, "Yeah, in knot theory, linking numbers in knot theory." I said, "Why are you interested in linking numbers? Why are you interested in knot theory?" He said, "Well, we are studying knot theory in medical school, and the professor talked to us about linking numbers, and I didn't understand what he was saying, and I don't think he understood it either." So I'm asking you, what are linking numbers? I said, "Yaakov, why are you studying knot theory in medical school? Yeah, what happened? Beersheba, they've gone crazy. Yes, what are they doing?" He said, "Well, sometimes the DNA in a cell gets knotted up, and depending on the characteristics of the knot, this can lead to cancer, it can lead to other problems, and so in order to understand the characteristics that can lead to those problems, we have to understand knot theory." I had to sit down. I was totally bowled over. What I had chosen, especially 50 years ago, exactly 50 years ago, because it is absolutely useless, is now being taught in the second year of medical school in Beersheba, and my grandson is studying it. It was really an emotional experience which is really mind-blowing. And this is what I want to sell to you. I want to sell to you that there's no such thing as pure and applied science, yes? That I chose it because it's so damn pure, yeah? And here it is, they ruin it, they apply it to trying to cure cancer and things like that, yeah. Okay, I promised Mrs. Zetrin, the Prime Minister, to say something about game theory also. She said, "What's game theory?" I said, "Okay, I'll talk about it a little tomorrow." So I'm going to talk about game theory also. Game theory is the same thing. It was started by John von Neumann in actually it was started by Borel, but Borel formulated, a Frenchman, Borel. It was formulated by Borel, the original problems, and then von Neumann proved the first important theorem in game theory in 1928, the Minimax theorem. Now, this at the time was literally a game, yes? It has no importance whatsoever, yes? How to solve two-person zero-sum games. Von Neumann was absolutely unaware of any possible applications of this. And then he met Morgenstern, Oscar Morgenstern in Princeton 10 years later, and Morgenstern, who was an economist, had become aware of this kind of problem from the economics end, and the meeting was, like two well, you take a sufficient two pieces of uranium-230, what is it, 239? Yeah, and you put them close together. I mean, this created this explosion, which was the theory of games and economic behavior. This was published in 1944. The meeting between these two people, the mathematician and the economist, created the theory of games, which is now, I think it's fair to say that it has become a very important, a cornerstone of modern economic theory and also economic practice. And it started from a game, from something which has absolutely no practical interest whatsoever. This was pure science when von Neumann did it. It has now become the cornerstone of economics. One last example, which has to do very much with Israel, with the development of Israel, with what we're celebrating today, 60 years of science in Israel. Ladies and gentlemen, Israel is the world's number 2 power in high-tech, in computers, specifically in computer technology. The world's number 1 power is California, number 2 is Israel, okay? And this is due to the school of that was founded. I'm not talking about a physical school. I'm talking about a school of thought which was founded by Professor Abraham Halevi Frankel, the first chairman of the mathematics department at the Hebrew University. Professor Frankel was one of the great contributors to set theory, axiomatic set theory in the 30s, the 40s, the 50s, the 60s. Set theory is a very abstruse, especially axiomatic set theory, is a very abstruse branch of mathematics. I wouldn't call it natural and easy to state. It is difficult to prove the things there, and it did seem at the time absolutely useless. And the problems of set theory and the problems that are related to Gödel's theorem and to Turing and that kind of thing, he raised a generation, Frankel raised a generation of scientists who became interested in what became the foundations of computer science. And this, I think, this is today what has made Israel into the number 2 power in computer technology in the world. So again, this very abstruse, this very abstract set theory led to the very, very concrete, very important computer technology that we see today. And it works the other way around also. You cannot have pure science which is not somehow rooted in applications. Von Neumann, who I mentioned before, said that once things become too removed from the real world, they will not work. So you have the thing working in both directions. The thing to do is to lead, to go to on the path that your curiosity leads you. If your curiosity leads you to a certain path, go and follow it. That is exploration in science. There's no such thing as pure and applied science. Thank you very much.